Okay, we should start. So today we're gonna keep on working on our Bayesian workflow and maybe get a head start on multi-level modeling. But first, do you have questions? Anything that's unclear, that was difficult to figure out in the assignment? Good. So I actually realized that I was discussing generative modelings, and I might have left a bit on the side with the kind of questions that we're asking. So I stole a graph from the third edition of Statistical Rethinking, and I'm trying to want to use it for a bit of discussion before we go into the Bayesian workflow, which is that so far we have been working in terms of how do we build a generative model? We generate synthetic data. We use that to validate the generative model. We might change the generative model to solve issues or to add a component that's more fit to what we're trying to develop. But we might sort of have lost why are we even doing that, right? And so real scientific project actually starts with an estimate. So with a scientific question that we're asking. So for instance, right, with the kind of models that we've seen so far, one could say, oh, in computational psychiatry, there are these assumptions that negative feedback is special compared to positive feedback. For instance, we might have that depression symptoms might be related to pathologically stronger reactions to negative feedback compared to positive feedback. And we might want to go and test it across a variety of contexts. Right? So our goal is really to figure out whether a certain kind of symptomatology co-varies and maybe even generates, it's maybe even be generated by the specific reaction to learning, negative versus positive feedback, right? So what we then go and work in terms of the generative model is we need to build, let's say, a reinforcement learning model that differentiates between negative and positive feedback, right? And we need to do all the kind of things that we are doing these days, right? So we generate the data, we build a stand model, we validate it extensively, we make sure that it works as it's intended to, but that's not the end goal, right? The end goal then is to actually have a different question, right? That is, can we condition the specific parameter that is the learning rate when we have negative feedback to, let's say, symptoms of depression? And that's the kind of things that you've been doing in previous courses, right? And we'll eventually get there. But we are, learning this new piece about the generative model, and that's why we sort of put everything else into parentheses. But this is only a piece of the bigger picture. Does that make sense? Yeah. So we'll get to do the kind of statistical estimates, comparisons between groups, correlations with parameters, and so on and so forth, right? Once we are very secure in our ability to build and validate our generative models. And then we will actually be able to use the whole apparatus that we're developing, not only on the generative model, not only on the single agent or the group of agents doing the thing more or less in the same way, but actually to the full statistical model that we build, that is to our ability to reconstruct accurately a difference in learning from negative feedback as modulated by different degrees of severity in depression. Okay, but where we are is a bit earlier than that. So we theorized models, we formalized and simulated generative models, that is from the model to the data. We are building inferential models in Stan that can make inferences on data, that is from data to model parameters, right? And what we started doing is trying to figure out how we assess these models, how we make sure that they're doing what we actually think they're doing. So we've been generating prior and posterior predictions. And to do so, we had to learn how to create the generated quantities chunk in Stan, where we can generate variables after the model has been fit. We did prior posterior update checks. So we were trying to figure out, given our prior, after having seen the data, how has our belief in a specific distribution of parameter values changed. And what we're going to do today is we're going to look at sensitivity analysis and parameter recovery and simulation-based calibration, which if I actually don't know if you've done in previous courses, power analysis. Did you? Some? It's not conceptually very different from that. And we'll see how it fits in the general framework. In a sense, power analysis is a very specific case of the things that we're going to do. And I'll explain what power analysis is when we get there, if you're not completely fresh on that. So this is, made it in white. Woohoo. This is the kind of code that we developed so far, right? We have the data. Not going to go through data, parameters, and models. You know that. But what we covered last time was the generated quantities. That is, we created a variable for the prior, so it actually gets saved, and we can use it for visualizations, which we called theta logit prior. It was sampled from a normal with a mean of 0 and a standard deviation of 1.5. We transform the theta logit prior into a prior that we understand. That is the one between 0 and 1. Probability space by doing inverse logit. And just for convenience, we also converted the theta logit of the model into a theta by doing the inverse logit. So it's easier to compare theta prior and theta posterior. We then ran a bunch of predictive simulations, right? So we have the prior parameters. We want to see what our expectations about the phenomenon at stake, how many times people are playing right, plays just from the priors. What are the patterns that the model is implicitly assuming, right? And so we created an array that we can call H prior. Can't remember what pred stood for in my head. Yeah, so they're the predictions. Maybe I just want to write pred. And we take a Bernoulli random number generator, which works with the logit, / faster. And then we give it, actually here I made a mistake. I corrected it in the code, but not here. And we give it the prior and the N of trials. Why are we using the repeated vector? Because last time I was just using a binomial and we were getting how many trials out of 120 generated a response of 1. But here I actually want to have the full sequence, because that's something that you're going to need if you're going to work with reinforcement learning or any model that has a sequential nature. So I'm just repeating the value of theta logit prior n times so that I get out an array of n of 0 and 1s. There's something that puzzles you, Christian.
I was thinking about, like, why do you need the sequence? Why wouldn't it be like you actually need the full sequence of just the previous one from the previous trial? is it more like a technical thing now?
Oh, so these are predictions from the prior, right? So what we want is the whole sequence of behaviors that we would expect from the prior only. So if we have a model like the bias agent, the actual sequence doesn't matter. We could just generate how many writes out of 120. But if we have something like reinforcement learning or a memory agent of other kinds, then what we want is the actual sequence, because it can generate patterns, as we will see, that can help us discriminate between different models. And then, given that we're dealing with a biased agent and we don't care about the sequence, in this specific case, I made a sum, so that we just know how many trials out of 120. We do the predictive checks from the posteriors. So after our model has seen the data, what has it come to expect? Why is that? Well, that's because our models, even after being trained from the data, they might have their own ideas. Let's see if I remember to bring the color. Yes. Right. So my always go-to example is this is your data from an experiment, has a peak at 250 milliseconds, and then a long tail. And you fit a very reasonable normal model. The expectations of the model after having seen the data, actually probably is going to be a bit more skewed, are going to be something like this, right? It used the data to the best of its ability, but it has some internal constraints, for instance, that the outcome follows a normal distribution. So given those constraints plus the data, these are the posterior expectations that you have, right? And knowing those allows you to better understand the biases of your models and if it's good enough or not. So this is exactly the same code as above here, but instead of using theta logit prior, we use theta logit, the posterior estimates of the theta. Sorry, got a weird sound from the Zoom. What if, and then what we add here is something that we're going to use later today. And I'm just putting it here so I don't have a million slides with different Stan code, but I'll explain it in detail. But the basic idea is that we want to calculate the log likelihood that each data point has related to the model. I'll explain it in a second. And the log prior likelihood. What is the log likelihood? If you remember, as we develop a model with a specific distribution of parameters, different data points might be differently fit to that model, or might be more or likely to be produced by that model. So for instance, right, in this example, these region of data points would be quite likely to be produced by the model. But these region of the data points would be quite unlikely to be produced by the model. For the people on Zoom, I'm just pointing to the long tail of a reaction time distribution, which has been fitted with a normal distribution so that the tail is completely out of the expected values. Right? And so this is something that we can use for some sensitivity analysis, but also that could be used to assess whether there are specific regions of the space that are not well described by the model. the L prior, and again, we'll see why it matters later, but it's basically saying as we have a prior distribution, let's say for our theta, it was something like this, and we have a posterior distribution, not all values of the posterior distribution might be equally likely given the prior. Right. Which is, in a sense, it's a measure of distance between the posterior and the prior, which can tell us how much is the posterior congruent with the prior and how far we've moved as we've seen the data. But we'll see in a 15, 20 slides where we're going to use that. This was just to show you what the full stand code that we need for today's tests looks like. So we added saving the prior, we added saving the prior predictions, we added saving the posterior prediction, and we added saving how likely each data point is given the posterior estimates of the model and how likely are the posterior estimates given the prior. You can see it here, right? It's exactly the same code as in the model. So we have that there's a Bernoulli logit LPMF, where a given data point is a function of the theta logit. But instead of just adding it to the calculation of the log posterior probability, we save it in a variable because we can do stuff with that. Stan wouldn't save it by default because you don't necessarily want to do stuff with it, but we want. The second is saying that the theta logit is generated according to a normal distribution with a mean of 0 and a standard deviation of 1.5, right? Which is the prior that we had above there, right? So we want to see how likely the theta logit is given that prior distribution. Oh, yes. So now we have the full overview on the code. We might not understand all the specific passages, and we'll get there. But do you notice any bad programming practice here?
I can't see it.
Yes. Well, so up there, we define the model prior, where we specify 0 and 1.5. Then in the generated quantities, we save the logit prior, specifying the values 0 and 1.5. And then when we calculate the joint log prior, then we use again the 0 and the 1.5. Right? Yes?
So this repetition, few manual edits.
Yes. Exactly, more than repetition. Yeah, so there's data or specific values that are hard-coded in the code in several places. So when we go and change our prior, for instance, we would need to change it in 3 different places. And so that's a bad practice. But luckily for us, what Fan allows us to do is to actually feed the parameters of the prior, the values of the priors as part of the data. Then we just replace the 0 with prior theta m, wherever it appeared, the 1.5 with prior theta SD, wherever it appears. And now we can both be more sure that we don't mess up writing those values, but also we could change our priors and not having to recompile the model, right? It's just, those values are just part of the data, which allows, for instance, to loop through different values and see which impact they have. Yes. Okay, last time we saw that those were the predictive checks, right? In red, we have if we run, I can't remember how many times I ran it. I ran it like, oh, that's 2000 because that's the posterior, so the number of posterior samples. If we run these 2000 predictions from every value in the prior and in the posterior distribution, we get that before seeing the data, basically all ends of playing right in the game are roughly equally likely, except the extreme ones. And after seeing the data, our model becomes quite confident that it's something between, I don't know, 75 and 100 something, when the true value is 80% of 120. It's like 80, slightly less than 85 or something like that. Not 96? Okay, thanks. And we also saw that if we were looking at the specific theta parameter, the picture was more or less the same, with the prior distributed all over the place with a bit of discounting, and the posterior being quite close to the actual value and much more confident. In this case, the two images are basically the same because we have one parameter that maps directly into the outcome. As soon as we start having more than one parameter, this is not going to be the case. Right? If we have a learning rate, it's not going to map directly to a specific number of times that right is played. Does that make sense? We'll see a model, a more complex model today. Okay. So the model so far seems decent, right? We check that our prior moves are not completely crazy. They seem to make sense. We check that once the model has been fed to a specific data set, the model is learning reasonable things and is kind of honing on the right value. What is missing? Well, the first, yes. Yes, why do we need a parameter recovery? What's the lack in this that would be covered by parameter recovery? Yeah, well, so I would actually go a bit more specific, right? Here, what we did is we took one specific scenario, an agent with a rate of 0.8. And we see that the model is recovering decently the parameter value of these very specific agent. But possible values of rate go from 0 to 1. And we have seen before in simulation that things can change a bit at the two extreme between fully random and fully deterministic, right? So we want to make sure that our model is performing decently, not just with that specific value, but across the full range of possible values. Does that make sense? This is one thing. Another thing is that in this specific analysis so far, we have made very specific choices, right? So we have made the choice that the prior should be a normal with a 0 and a 1.5, which seems sensible, right? but how much are our results depending on that specific choice, right? Another choice that we made was 120 trials, right? That was a number that was somewhere in the slides, right? And we just follow it blindly. But how much of an impact is that specific number of trials having on our ability to infer the correct parameter values? And especially if we're smart and we build our models before running our experiment, right? These can be a vital thing to know in advance, right? If we can get away with only 30 trials, why run 120, right? We can either let the participant go home free earlier, or we can team up with somebody else and give them 2 experiments instead of 1. But if 120 is actually not enough and would need 240, we need to know that in advance. Does that make sense? So we have only looked at the very specific choices that I have spoon-fed to you without questioning them. And we have only looked at a very specific value to see whether we can recover it. So what we're going to do today is to actually expand in order to do systematic checks all over the place. Yes.
I think I have 2 questions. So one is, would you actually, like in the best practice, this makes it sound like you actually make models for doing experiments?
Yes.
To make sure that you have enough trials.
Yes.
Okay.
Or that you're making people play with the right agent. So for instance, well, I don't want to run too fast. There's something that comes later, but the idea is now we have all these agents playing against a biased agent. Is that the most obvious opponent that they should have? Are we really capitalizing on what we could otherwise be doing? Are we really getting the maximum information from these 120 trials? Right? There's also something called Bayesian optimization, which is a technique that you can use to optimize the information that the model is getting by calibrating on a trial by trial base which stimuli to give to the participant, right? Or a priori, optimizing the sequence of stimuli that on average gives you the most information. So here is just a question of gaining new tools to actually not trust that the model works with these choices, with these parameters, but doing a more systematic assessment. Yes?
So this might go a bit beyond, but I sometimes feel confused on what goes wrong when stuff do not recover.
Yes, we'll get there. So these has 2 aspects. One is how do we see that? And the other is what the heck do we do? And today we have an example where something is not recovering. So by the end of today, we'll have a specific example. I'm not going to derail it too much now, but remind me of that if I don't cover it in enough detail. So right now, I didn't want to sort of overload you with stuff that doesn't work. Like we'll just get it to run. And as we implement more complex models, we'll see all the stuff that can go wrong. Another thing that I want to add is now these that we learned is not going to be overridden by what we're going to learn next. These techniques are very useful because you don't want to test your model on a million different parameters before you've checked, even if things work on 1 parameter values. Second, once you have fitted the data to the model to empirical data, these again become very valid and reliable because in that case, the data set is already there. The choices have already been made, and you want to know how well the model is doing given those hard-coded choices, right? So let's start from prior sensitivity checks, right? We made a choice of prior that seemed to make sense and seems to be good, but we want to be sure that, or at least we want to know how much it's affecting our ability to infer. Right? So we can define a range of reasonable values, and we can iterate over those values. So we can evaluate changing the prior mean theta and changing the prior SD theta. Take 30 seconds and think about what changing these two values separately means. Right? So when we change the prior mean, we're changing the mode of the mean. When we're changing the prior standard deviation, we're changing the variance. And these two things are telling the model very different things. Anybody wants to pitch in? Yes. Yes, so the standard deviation, just repeating it aloud, tells us basically how confident our prior is and how open it is to be changed. Yes.
Bias in logos, right?
Yes.
Yeah. So I think you made a point last time
Yes.
that when we do this benchmark, if we do like 2 flatter prior,
Mm-hmm.
it's going to push the, like when we go through the inverse logic, it's going to do this U shape.
Yeah.
So if we make 2 flat or 2 high standard deviations, that's going to expect extreme values, right?
Yes.
Yeah. So I guess that would be the thing, increase standard deviation.
Yeah, exactly. So given that we're working in a space that is non-linearly transformed, right? Log odds, but really what we want is a 0-1 space. We should be careful about how our changes in the log odd space transfer into the probability space. But so that's also why we want to do these tests. But if we think about the probability space, or the space in which the parameter actually is, the more uncertain it is, the less impactful on the inference it is, right? What about the mode? So if we move the mode, what are we doing to the model? Yes?
We are biasing it away from 0.5.
Yes, exactly. So we're telling it that we expect there to be a bias in a specific direction. And again, right, here, we don't want to do that, but in a reinforcement learning, we might find a meta-analysis that tells that known psychiatric patients tend to have a learning rate for negative stimuli feedback, which is about, I don't know, 0.8 with a standard deviation of 0.1, right? And it might be smart to use that because it's information that we have, but we want to test how much it would impact our inference. Does that make sense? Yeah. So here is just the stuff that I showed you before. What we do is we create a prior mean that has 3 possible values in log odd space, right? Minus 0.5, 0, and 1.5, right? It believes there to be no bias, that's a 0, or it believes there to be more bias towards the left or more bias towards the right. The standard deviation starts at 0.5 and it goes all the way out to 3 in 10 steps or 10 values between 0.5 and 3. I put it in a grid so it gives me the full combination of these values. Then I create a function that has the prior value for the mean and the standard deviation and a seed, which we can ignore for now. It takes an observed data list, like our stand data, and it updates the specific values of prior M and prior SD. And then we fit our model to that just updated data list, only one chain, because it's, we need to run a lot of those. So we just want one, some parameters here, and then we extract, we're still within the function, from that fitted model, our theta parameter, which is what we're interested in. And we create a table that has the theta parameter and the specific value for prior, mean and prior standard deviation, so that we can then feed that function to a parallel process, right? Because we're starting to get into models that if we don't parallelize would take too long. So we tell the computer that we want to use as many cores as we have on our computer, but -2, so that it doesn't hang. Like there's room for whatever else we're doing. One for the operative system and one for you watching Netflix or being on Facebook while the model is running, right? And then we use future PMAP, which takes the prior grid, takes the function that we've given, right? And then it just runs it parallelly on as many cores as we can use, right? And then what we have is we have a list of all these results, a list of tuples, and we're putting it together in just one tuple, big tuple. There's many other command in fir, which, for instance, could spit out already a tuple, but I had this code already from last year and I didn't change it. But I made it black and white. Yes. So what we see here is the 3 prior means, the 10 possible value of prior standard deviation on the x-axis, the estimate on the y-axis, and you can see the estimates are spread out because I'm taking the full posterior from the model at each data point. And the dashed line is the true value in the simulation, right? So what are you noticing here? Yes?
They all seem to underestimate a little bit.
Yes?
But however, with larger of trials, larger they all seem to with the one standard deviation.
Yeah. Yeah, it's 1 standard deviation, yes. Okay, so I think I'm going to generalize your observation. There is an early region in all the priors where the prior mean does not match the true, where with high confidence in the prior, low standard deviation, the inference is strongly impacted. Right. This left part in the first 2 panels. We also have that after a little while, actually around 1.5, we're pretty sure that the inference has stabilized. Making the prior less confident does not change our inference, right? Which is something that we can use in a paper, right? Or in a report to show that our choice of prior is not unduly influencing the inference. We also see that there is a systematic bias in the model where we might be slightly underestimating a 0.8 value. And we've seen before that what happens is that since we have that slight discounting at the boundaries, we've seen that before, but here it's actually, even when we have, very skewed priors that say it's either 0 or 1, we still get that issue. So the model is not perfect. It's likely underestimating the value of 0.8, which means that if we were running something at 0.2, it would be slightly overestimating. It's shying a bit away from the extreme. In this specific case, right, a rate of 0.5 or a rate of 0.8, they are the same for us, right? But sometimes we actually want to be in the region in which the prior is affecting our inference. For instance, when we're running a model where we want to know whether the data is telling us, I don't know, whether ibuprofen is causing autism, right? And we want to start with a slightly skeptical stance. The data should overwhelm us for us to believe in that hypothesis. Or again, if we have a regression with 10 predictors, right, one of them is bound to be by chance significant, right, to show a trend. So we want to be in a region where the priors are skeptically affecting our inference. They are regularizing. They're telling the data that they should work a bit harder for us to believe in that, right? So having a prior which is in a region of where the prior is influential is not necessarily a bad thing, but we want to know that. Does that make sense? Okay, doing this is fine with this model. It runs really fast if you try the code. But as we get into more complex models, where a model might take 6 hours to run, and you want to run, I can remember those were 30 different models, even parallelize is going to be kind of a pain, right? And if you want to be more systematic and run more possible values, then you're going to be in trouble. And if you have a model that takes 2 weeks to run, right, of course you should parallelize it, but it's still going to be a pain to do these kind of assessments. So there's something called prior sense, which is a tool that has developed computational tricks to actually estimate the sensitivity of your model to the prior and to the likelihood without having to refit the model a million times. And it does so by using what is called power scaling, which is you cannot see it, but here there's the posterior, the probability of theta given y, or given h in our case, is proportional to the likelihood, right, the probability of the data given your model, times the prior, the probability of your model or of the values of your parameters. And what these technique does is to put an exponent on top of the prior and a different exponent on top of the posterior, which we will see in a second what that means, right? Yes, so what we do is, if we put an exponent that's below 1 on one of these parameters, we decrease the impact that that component of the model has on the posterior, right? So how do we do this in practice? The idea is that just a second. Yes. Yes. As we calculated, we fitted our model, we have that so we have a posterior of theta, right? Which has a bunch of values, the posterior samples, as many times as we sample the posterior space after the warm-up. So if we had a warm-up of 1,000 and iterations of 1,000, and we ran 2 chains. The warm-up is thrown away. We have 2,000 posterior samples, right? Each of these posterior samples can be compared to the prior. Right? So we can say these posterior values, let's say it's a 0.7, how likely is it given the prior? Right? And here we would have that, for instance, 0.1 is going to be the least in this set of 3, the least likely given the prior, while 0.5 is going to be the most likely given the prior, right? If you remember, it's centered at 0.5 and it decreases slightly the farther you go. So now we have that this value is the least representative of the prior, and this value is the most representative of the prior. If we downweight this, say we give it a 0.8, and upweight this, let's say give it a 1.2, we are decreasing the impact of the prior on the posterior inference. Because we're taking those values that were most compatible with the priors and giving them less impact on the inference. And those posterior values that were least representative of the prior and give them a higher impact on the inference. And we can see how much that changes our posterior. Does that make any? So this is the first time I'm teaching prior sense, so I'm actually curious to see if this makes any sense. Good. Yes.
I don't think I understood how you would change the weight of them, like that you just described, like suddenly our.
Yes.
It was the prior right of 0.5.
Yeah, that was our prior. Yeah, that's the prior that we have, like the one that's roughly like this, right?
Wait, 0.8?
Oh, not the value, but so here, when we look at how the distribution looks like, all of these have a weight of 1, right? All of these values are taken at face value. Here, we're downweighting or upweighting them. And that means that this is going to count as 1.2 points. And this is going to count as 0.8 posterior samples. Right, so we're going to have that the distribution of the posterior, well, let's actually make a better example. Yes. Let's take a more informative prior, so it makes more sense. So if we had these prior, and then we have these posterior, right, where the prior is centered, is quite confident, and the posterior is basically the same shape, but shifted to the right. So we're going to have that all of these values that are roughly overlapping are going to be downweighted because they're representative of the prior. And the values that are not covered by the prior are going to be upweighted. They're going to count for more, right? Which means that the shape of the posterior is going to be shifted more towards the right, right? Because here, this counted for 1, but now it counts 20% more. So we're going to put a lot of the 20% more mass at that, 20% more probability density for that specific value. And we're going to put less. Now, I should have used different colors, but less in the peaks that were very compatible with the prior. Does that make sense?
Yes, and that reminds me again, what do we then use that's output for, like what?
Yes, that tells us that the prior has affected the posterior, right? And that if the prior had been broader, we would have had a different posterior. And we can calculate that without refitting the model. Because we already have these, we just need to change the weights. Then we can make this even more extreme and say, oh, instead of a shift in 0.2, here it's actually going to be 0.6, and here is going to be 1.4. And then we see, how much it's going to change again. And then these one, since it's also a normal shape, right, it's not going to move too much. It's going to stay roughly here, like it's going to in the space in which it was shifted. But had it had a long tail, right, it would have moved a lot. And that meant that those results were very sensitive to the choice of prior. While results that don't move much, they're not very sensitive to the choice of prior. Yes?
Do this technically, like, does it use a histogram sample?
It technically actually used the reweighting.
But how? Without resampling.
Oh, because you have the posterior distribution, the posterior samples.
Yeah.
You can look for each value, how likely it is given the prior.
Yeah.
And then invert that and turn it into a weight. So that these one, now it counts as one posterior sample, but it's going to count as 1.2 posterior samples, or 1.4, or 1.6, or whatever.
Okay, so what it does is it just takes the bins of the posterior histogram, and then it integrates the prior over that area and multiplies the.
It actually doesn't need to integrate, because you can just, since these are counts,
yeah,
right, you can actually just say, instead of counting 1, it counts 1.2.
Yeah.
And then you simply count per each value or each bin how many posterior samples there are after you reweighted them.
It doesn't need to integrate the prior, right?
Nope. It can just use the, what is it called? It's a function that, given the definition of the prior, can tell you the probability of generating a given value. It has a name. It escapes me. Yes. And so basically, by doing this reweighting more and more extreme, you can see how much the posterior is going to change. And then you can use Kullback-Leibler distance between the two distributions, for instance, to calculate how much they changed. And then you can see the more you perturb the prior by changing the reweighting of the posterior, how far would you push the posterior? We can do that not only for the prior, we can also do that for the likelihood. We can see, given each data point, we have a bunch of data. How likely is the data? Let me just get it right. Given the posterior. And for data that fit well the posterior, we can downweight them. And data that don't fit well the posterior, we can upweight them. This tells us, right, how impactful the data that we have is on the inference. If we have data that are very well within the predictions of the model, then the data size is not going to impact it too much. But if we have data points which are outliers, which are a bit all over the place, these are going to be upweighted, and that's going to change the shape of our inference. And that suggests that either we should change the model to better account for these outliers, or that we should sample more data, right? We should go out and collect more data, I should say. Right. So this is a trick that can be used to, in a very computationally efficient way, assess how much our results are impacted by the specific choices of the prior and by the specific choices of the sample that we have. And so the way that then it calculates the diagnostics of these tests is it looks at whether the posterior mean shifts from where it was, calculated in standard deviation of the posterior mean. So it's a standardized mean difference. A value below 0.1 is usually taken as a sign of robustness of your inference. Is not going to be shifted a lot. A value of above 0.5 tells you that, for prior sensitivity, that the choice of your prior is very influential, that your results are very sensitive to the choice of prior, so you should be prepared to motivate your prior more or to change it. It's fine to keep it. You just need to be aware that your choice has had an impact and you need to be able to motivate it. If your likelihood, right, has a value below 0.1, again, your inference seems to be robust, given that your results, that your sample is representative of the full population, blah, 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 usual stuff. If you have a value above 0.5, then it tells you that very likely, if you went out and picked a different sample of the same population, you would still get different results, right? And that might be a problem. And this is the code, but we don't need to go through that. We'll look at the plot and then we'll get a break. And so here in our theta, we're looking at how much the posterior is changing given the reweighting of the prior. And as you can see here, right, where you can see the 3 different values of the posterior with 3 different changes in the weighting of the prior, things stay more or less on top of each other, and the uncertainty is also more or less the same, and the 3 distributions are very much overlapping. So it seems that our model is quite robust to the area, the region of values of the prior that we've chosen. But when we look at the likelihood, we get something different, right? The confidence of the posterior is changing quite a lot, like the height of it is changing. But the mean is not changing that much. Right? So what this is telling us is that the more data we have, the more confident our prediction is, but that we're not really biasing it in terms of the mean. Does that make sense? Okay. This is doing more or less the same thing as the prior testing that we did before the prior simulation was doing, but he's using a trick that is going to come in very useful once we have complex models. And now we get a break. Okay, we should start again. So now we had a look at how we can more systematically test the impact of the prior and of the likelihood. And what we can do now is to actually go and see if the agents, the data that we're trying to reconstruct, come from different parameter values. And the model actually makes sense of that. And so just like before, what we have is we create a function, right, which takes true theta, point it up there, right, to generate some data. Then it makes the stand data with our fixed priors. Now we sort of happy with that. Then we fit the generative model then we extract the theta, and we make our table. Right? We parallelize saying, oh, what if we had 30 trials, 60 trials, 120 trials, 240 trials? And what if the theta is 0.5, 0.7, or 0.9? And I'm starting at 0.5 because the distribution is completely mirrored, right? So if we go at 0.3, it's the same thing as 0.7 would be, just in the other direction. So we have a random agent, a mildly biased agent, and a strongly biased agent. Then we parallelize as before, and we get the outcome out. And so here we can see for each of the experimental setup, 30 trials, 60 trials, 120 trials, 220 trials, we can see how well the posterior estimates are doing. The dashed line is where the posterior mean should be. So again, it's nothing, revolutionary, but what do you see there? Yes.
To cover the parameters, and it's certainty increased the number of
Yeah. Okay. So to be more precise, what we can see is that the ranking of the parameters is preserved. So if in the true value, in the values of the simulation, the true theta was lower than the next, right? We can see that the posterior means reflect that ranking. That with 30 trials, it's pretty imprecise. Right? Things are, well, this is one run, so we shouldn't generalize, but we can see that some are above the line. And the uncertainty is pretty big, to the point that the uncertainty is actually overlapping with the posterior means of the other estimates. If we go to 60 trials, the ranking is again preserved. Perhaps it's stronger. Again, I've run these once. We should run it 100 times. And that the uncertainty is shrunk in a meaningful way, right? And as we increase, right, we see that this trend becomes stronger. The dots become more aligned with the diagonal lines, and the uncertainty becomes smaller. So this is actually very similar to what you do. It's actually a kind of a power analysis, where we are saying, given a different amount of data points, how precise our estimation becomes. And if we were to put a threshold, let's say the true value should be within the 95% of the posterior sample distribution, then we could say, how often does the estimate captures the true value with 30? So what's our power in that, if you want? With 60, with 120, with 240. Right? And if we were to run, more complex model, where then we would want to look at differences of these size, right? We could count, once we subtract all the posterior samples of these from the posterior sample of that, right? How many times, how many times does the simulation capture the true value of the difference? Yes.
When you test the power analysis for like experiment, what sort of is the standard for choosing the amount of trials necessary? Like, do you need to have an amount of trials where no trials end up outside the 95% confidence interval, or is there some sort of threshold that is generally used?
It really depends on your question, right? So if you're running a frequentist analysis, what you want is that your p-value in case of a true difference should be 0.05 or below. That is, that you would reject the null hypothesis at least 95% of the time. In Bayesian analysis, sometimes we talk about precision analysis, And we could say, oh, we want the true value to be within the the credibility intervals 95% of the time. But it really depends on what you're trying to do with those results, right? So you could say, oh, this is actually about a clinical trial. Then suddenly 95% intervals, they don't feel as precise, right? Because you want to really capture which impact these is having on whatever symptom you're trying to attack, right? If, I don't know, you're running something to better understand a very rare clinical condition, let's say Moebius syndrome, where people are born with their faces paralyzed, right? Where there's about, I don't know, when we went and looked at teenagers in Denmark, we could find 5, right? So there, it doesn't really matter how precise, you just want to contribute that information to the literature. So there is no standard. Of course, if it's for a paper, right, then using 95 intervals is a nice rhetorical trick because it sort of relates to what a lot of reviewers are used to. But you should think about what's at stake and what's important. Yes, do you have a question there? Yeah. So does this make sense, right? So from this plot, we can start asking if we recover the parameter values, right? We could try to figure out how do we quantify the goodness of recovery, right? As in this question was raised. And people have done it in many ways. So some people do a Spearman or like an ordinal correlation between the true values and the mean of the posterior estimates to see whether the ranking is preserved. There's people who use the intervals and quantify a power-like feature of the design. Yes, that's it. And that we would need multiple seeds and multiple simulations to see these properly, right? Because now this uncertainty is due to the uncertainty of the posterior estimates, but we shouldn't conclude that with 30 trials, the algorithm systematically overestimates the rate. That's likely to be a chance. And if we were to run 10, they would be some above, some below. Okay, so these parameter recovery is great. It's very useful to get a grasp on what's going on. It tells us a lot about how many trials or participants or whatever other design choice we could use. How does that impact the inference? But it has 2 shortcomings. The first one is the one that we already talked about, right? As soon as your possible choices start growing and the complexity of your model start increasing, then running a lot of simulations and fitting these models is not feasible. The second is that there is a strong affordance here in just looking at the mean of the posterior, right? That's where we're focusing. And this test is not telling us much about the role of the uncertainty in the inference. And so this is where a new tool has been developed called simulation-based calibration, which is about calibrating the uncertainty of the posterior inference, telling you how well is the posterior inference, how well is the uncertainty in the posterior inference actually capturing the data? Are you underconfident? Are you overconfident? Are you biased in one direction? And so, for instance, we want to know that true values are not consistently in the tails of the distribution, or that they are not consistently biased, so higher or lower of the estimates. And so what this procedure does, it takes the prior, it samples a value from the prior, it generates a simulation, and then it fits the model, and then it ranks the truth. What does it mean to rank the truth? It means that you have a posterior distribution of theta in our case. And by drawing the posterior distribution, you are ordering the values, right? Because in the posterior samples, you might have 0.8, 0.7, 0.9, 0.2, 0.3. They're not in any specific order. But here you're ordering them. And so you have that this one is the first, and this is the second, and this is the third, and this is the fourth. This is the fifth, and so on and so forth. Then you take the true value, say it's here, and these might be, I don't know, in the, if we split it in 100, it could be at the 80th position. Right. Then we run the process again, right? And we would expect these to happen. The true value could happen in a different place in the posterior inference. And so if the model is biased, meaning if we are always overestimating the value, the true value will tend to be in the early rankings, because the bulk of the distribution is going to be higher than the true value. If we are underestimating the true value, then we're going to have that the true value is going to be in the early ranks. Did I mix it? So if we're underestimating, sorry, it's, the true values. So then I shifted the order. Sorry. Okay, let's restart, right? So you understood the procedure. We rank the posterior samples, and then we look at where the true value falls. We run a new simulation, and we do that again. And so if we have that the true value tends to be overestimated, right, then we would have that the histogram of the positions in which the true value happen is going to be higher in the early positions, right? If we have that the value is underestimated, then we're going to have the opposite situation, right? We're also going to have that if the model is overconfident, right? It has very narrow confidence intervals. It's gonna put the true value most often at the extremes, because the mean, the posterior density is going to be moving a bit around according to the simulation. But since it's too confident, you're going to have the tails overrepresented. If the model is underconfident, meaning it has very broad confidence intervals, the true value is going to be most likely to fall in the middle, because the tails are so broad that the true value is not going to be there. Right? So the histogram is going to look like a U with the bottom up. While if the model is underconfident, you're going to have the U with the bottom down. Does that make sense? Yes.
How would a histogram look after calibration where we have one that's neither over nor under, like really good one?
Yes.
Would it be like a uniform?
It should be a uniform distribution.
Yeah.
Because what your model is telling you that if your model assumptions are correct and the data is representative of the true population, then 95% of the time your true value is going to be here, right? But it doesn't tell you where. So that's why you're going to get a uniform distribution. Good. Yes, I said that. Here is the code which does that. And here is the simulation from our model, right? Where we get the histogram, we get that it's not very easy to see whether it's uniform or not, right? Even if I run it 1,000 times. Therefore, the program, the package is also giving us two rhomboids that tell us that if the majority of the bars are within that, we should consider it a uniform. And below here, we see the cumulative distribution just as a comparison. So in this case, we see that there is one bin that probably by chance is going above, but there is no obvious bias. If this was a model that I wanted to use concretely, I would then go and run 10,000 iterations instead. This is not as smart as prior sense. It has some tricks to optimize the computation, but it's still refitting a bunch of times. No, that was, yes. Okay, yes. What we've seen now was that the model is sampling from the prior, and it's telling us whether the model is well calibrated in the parameter space defined by our prior, which is, good because we're testing our assumptions, but we might also have that once we see the data, the model is moving out from that region of space, right? And therefore, we become more interested in whether the model is well calibrated to make inferences in the specific region of parameter space that is defined by the posterior. The good thing is that we can just replace where we sample the initial simulation and not sample from the prior, but sample from the posterior. And in this case, since I was running it just before coming to class, I ran fewer, but it also looks pretty calibrated. Does that make sense? Good. So now we've seen the Bayesian workflow that we're going to use through the rest of the course. There's other stuff that we could do, but that's like, I think, a very solid setup. We want to see how it applies to a more complex model, right? We calibrated our biased agent, but what if we give the agent some memory? So we pick a perfect memory model in which the memory at each time gets updated by, in a sense, the predictive error divided how many trials we've gone through. Because the more trials we go through, the less one trial is going to shift our estimation of the average bias in the biased agent. We could also do something else, and I do that in the course notes for chapter 4 with something that's closer to reinforcement learning, but now we'll just stick to the memory one. So here is the DAG representation. It's not the most beautiful one, but we have the biased agent. And what we say is that the rate at which the agent is going to play right depends on, let's say, a general bias of the agent, a tendency to pick right because they're right-handed, plus their estimate of how often the other is being playing right, which might be moderated by a beta, how strongly the agent is determined by the memory of what the opponent has been doing. Right. So we have that rate is actually deterministically calculated by using a memory state, a bias, and a beta. Yes. And I'm actually going to skip that because I want to get to these. So we build the model, and you can check it in the course notes. And then we run our Bayesian workflow. So we see that our prior on the outcome scale is kind of sensible. All the values are represented. Extreme values are discounted. The posterior seems to capture the data from our simulation. It's a bit broad, but we're doing 120 trials. So this seems perfectly right. Then we look at the prior posterior updates. So when we look at the beta, so the coefficient for memory, we can see that the prior distribution on the logout space is normal and broad, and that the posterior, after having seen the data, has moved from the prior distribution, has become more confident, and it's very centered on the true value from the simulation. But when we look at the bias, this is not what's happening, right? We can see that the posterior is only slightly more confident than the prior, that the posterior mode hasn't moved a lot from the prior, and actually it has moved away from the true value. The fact that it's very insecure, it's telling us that the model hasn't been able to learn from the data properly. Let's keep this in mind. What you think that is, why hasn't the model been able to learn from the data? This is one of the cases where things go wrong, right? So let's think about the setup in which the agent has been simulated. So what we have is an opponent that has a rate of 0.8. And we have an agent which has two components, a bias and a memory coefficient, memory beta. And as the agent plays, what we will see is that the agent will 0.5, 0.8 will tend to converge towards the 0.8, right? Because it's learning from the other agent. And with some noise, over time, it's going to get a better and better estimate that the running average of the opponent's moves is 0.8. Yes?
Is it perhaps because the more memory the agent has, the less likely we are to actually recover the bias because it learns very quickly? Or
Almost. I think you're almost there. Or maybe I'm, but I think there's a second. What, sorry?
it could also be because the other agent plays 0.8.
Mm-hmm.
And then our agent will have less uncertainty about which hand it plays more often.
Okay, so let's take, I think there's a piece missing. So what Martin is saying very rightly is the agent will learn what the other is doing. It's a pretty extreme value, so it can learn it pretty quickly. And then it will produce a bunch of ones, right? And 20% of zeros, something like that. However, that very same behavior. So would be an agent that has a bias equals 0 and the beta equal whatever, 1, will produce that behavior. But what if you have an agent that has a bias equal 0.8 or whatever it is, and a beta equals 0. You're going to get a behavior which is very similar to the previous agent. Or you could have intermediate value where, the bias could be 0.7 and the beta could be 0.5. Again, it would already start with a positive bias. And then even if it has a lower memory coefficient, it's going to get there. So out of the 120 trials, there's going to be very few trials that discriminate between these different agents. That means that the parameter values is largely unidentifiable because moving one of the parameters in one direction can always be compensated by moving the other parameter in the other direction, right? So what we have is a scenario where there's just not enough information for the model to differentiate between different underlying parameter values. How would you go to solve this? Yes.
Maybe make the same agents the table task multiple times.
Yes. So we want to change the experiment. But first, I'll just show you the rabbit hole where I was going a few years ago. That was, oh, you know what? That's because these two parameters are correlated, right? So what I'm going to do is I'm going to plot their correlation. So here I have the value in the posterior sample for the bias. Here, the value in the posterior sample for the beta. And we can see that they're strongly negatively correlated. Right? And then I was saying, well, maybe I can solve that simply by having more trials. Right? More data should give the agent enough information to separate those. Right? And actually what happens is that the more trials we have, the stronger the negative correlation. Also because these few trials at the beginning, they count less and less in this big thing. Right? So what we need to do instead is, as Martin was saying, we need to change the context in which the behavior is produced. If bias and beta can conspire to give the same behavior in a bunch of different parameter values configurations, maybe we need to mess that up. So what we can have is the agent that plays against an agent with 80% probability of playing right, and then midway through the trials, it shifts to a 30% probability of playing right. And that's something that in learning literature, this is called reversal learning. And that means that suddenly the bias is not able to explain this sudden shift. Right? Or it's not sudden, it depends on the memory value, but it's not able to explain the shift in behavior. And how fast the shift in behavior happens in our agent will determine how strong the memory is. Right? So that actually the data make the model identifiable. Yes.
And yeah, that makes a lot of sense. But then what would you do if you already have data that wasn't put into the design?
Well, this is unidentifiable. Like you need, so what you can do a few things. You have a big problem, but you should declare it. But the first is, what do you care most about? Do you care about the bias, or do you care about the memory? For instance, in most cases, you really wouldn't care too much about the bias. So what you could do is you could put you could remove bias from the model. and then see if the agent is generating data with different bias and memory values in the context that you're testing, would the model be able to reconstruct the memory, which is the one that you care about? Because now it doesn't have bias, it can get confused with that, but it will create systematic biases in the estimate of the memory parameter. You could play with the priors. So for instance, you could put a much stricter prior for bias at 0.5, so that then memory is given more space to move around. So there are a few things that you can do, but that's where it's very good to think of the model before you collect the data, right? Does that make sense? Good. And then I'll just very quickly show here we run the power scaling sensitivity. And again, we can see that there's quite some sensitivity to the prior, which is the top one, because as we change the prior of one parameter, right, that will affect the estimates of the other as well. Yes, Martin?
I checked one of the files, the real data that you uploaded.
Yes.
There I also saw that it was switching between random or like bias random point.
Mm-hmm.
Shift. Is that also because of this?
So it depends on the data set. If it's the schizophrenia data set, yes, it's because there's a long literature that tries to separate these things. Yes. It's also people didn't have these kind of models, so they were just saying, in this scenario, how many errors are they making? In this scenario, how many errors are they making? And so that's also, you want to do the reversal learning, because then you can see, for instance, how long after the reversal do they play consistently with the previous strategy, right? So you can operationalize a theory of a cognitive process with, dumb measures, if you want, just by manipulating the experimental setup. But we can do better. We can have the sophisticated experimental setup and the models. Yeah. And these are the histograms for the SPC. And then we'll stop here, and next week we'll tackle multi-level models. Yes?